Welcome, calculus students, and we're getting into the cross sections for calculus here. Usually this is the time of year where we do this really cool project where we make the actual shape. As you can see, it looks like this one might be squares, this one's rectangles, this one looks like it might be right triangles. We'll get into that, and then semicircles, and we'll go through all the context of everything, kind of explain everything. All right. So if you notice here, I have this split up into like a table type method, and I'm going to try to fill in the blanks. I'm hoping my handwriting is not that bad and you can read everything. I'm going to scoot it over so I can have a little bit more space there. And so basically, make sure you organize everything, make sure you keep everything detailed, and I'll go through it step by step. All right, so the first part, we're going to do the first one is squares. Now, I like to draw the side view of the graph. And what I mean the side view, like when you look at this picture, this base here is the height of it. This base is the height of it. This base is the height. This is the y-axis. It's almost like the x-axis is coming straight at us. It's coming like at a point straight at our direction. So if this is going to be a square, whatever this length is going to be the same, so this is also going to be y. That means that this area equals y squared. So the only thing that changes on our integral from a to b is going to be, and I'm going to just refer to as a function as f squared, f of x, the function that we're doing here, the y value, dx. That's how you find the area of every single one. So you're still going to set up the integral and just put it squared, and that will find the area of it. Now, let's do part B. I'm going to do isosceles triangle, so I'm going to write that out. Isosceles triangle. I'll just put it that way. But it's key that you understand that the leg is on the base. And real quick, I should say that this is a right isosceles triangle. Right isosceles. So what the side view is going to look like, just a second, I'm going to erase a little bit there. The side view is going to look something like this. Now, if it's isosceles, whatever side this is, this side's going to be the same. So if I was trying to find the area of that, it would actually be half of base times height, which is actually half of y squared. Let me try to write the integral for that. That's 1/2 integral. I'm not going to put the upper and lower constraint. I will assume that you know that, of the function squared. All right, let me move this up a little bit so we can keep going. Oh, let me just say why I did that one second. You should notice between the square and the right isosceles here, technically, if I cut this in half, I would just have a isosceles triangle. It would be this image here. So if you notice, the integrals are not really much of a difference. This one's squared, this one's squared. This one's only half because it's half of a square. Not too surprising. All right, part C. Part C, we're going to do the equilateral triangle. Equilateral. Wow, hope you can read that. So what this looks like is that all three sides are the same. The distance from here to here is y. Now, that's not too helpful because what I need to do is take my picture and actually just cut it in half. So once I cut it in half, it'll be y over 2. Now, think of this as a 30, 60, 90 triangle. Whatever the short leg is, the hypotenuse is 2a, not helpful because I want the height. The long a is a squared root of 3. As an example, if this is 5, this is 10. If this is 5, this is 5 squared root of 3. You should know this from geometry. So if we know that this base, just half of this base here, is y divided by 2, that means this height is y divided by 2 square roots of 3. Whew, I hope you can read that. So meaning that the area, and I'm going to write the area below here, is half of base. Now the base is the whole triangle, so I got to go back and reference to the whole base, times the height of the triangle. That's a 3 inside my square root. Hope you can read that. And so the final integral will be, and technically this, whenever I multiply y times y, that is the f of x that I'm writing on the inside. I'm just changing it to a function notation. So whenever I write the rest of this, square root of 3 over 4. What you should start to kind of understand now is that you're still going to do the area the exact same way, but now if I say equilateral triangle, you will use this formula. Just kind of make that connection going, oh, so listen to the keywords on this, all right? Let me go through. Let's do the isosceles triangle with the hypotenuse on the leg, I'm sorry, on the base there. So this is isosceles again, an isosceles triangle, but this time the hypotenuse is on the base. Unlike I think it was part B that I did, the isosceles, where the leg was on it, the side view of this will look something like this. So that's still a right triangle, just that these two sides are equal to each other. This length down here, from here to here, is y. If I measure straight down from here, well, I just made another 45-45 triangle. And again, what you should know about this is going to be y over 2, because it's only half that distance. That means this side is y over 2. So if I was trying to find the area of a triangle, I would take half of the base would be y, of the height, well, the height was this, y over 2, so the integral is going to be f of x squared dx, and it's going to be 1/4. I hope you can read that. And that's the integral again, isosceles, right triangle with the hypotenuse on the leg. All right, let me scoot this up. We have two more that I want to talk about, a semicircle and a quartercircle. So then this one is letter E. Is that correct? Is that letter E? Yeah, letter E. So looking at this, the semicircle is just a half of a circle, as you should understand. The cross view would look something like this. The whole distance here, let me get a different color here, this is y. Now, whenever I'm trying to find the area of a triangle, I only want the hypotenuse. Well, the hypotenuse on that is just going to be y divided by 2. So if I'm trying to find the area of it, and you should know area is pi r squared, it will be pi y divided by 2 squared. So whenever I write the integral, this squared is still going to go to the whole thing, so it's still going to be f of x squared on the inside. But on the outside, it's going to be pi over 4. And the reason why it's pi over 4 is because it's going to have pi and then the 2 squared, which is 4. One last one, and then I'm going to stop with this. Basically, I wanted to make a video just on how to come up with the formulas. They're not that difficult. Quartercircle. So the quartercircle will look something like this. It'll just be quarter of the circle. So this whole base will actually be the radius. So actually the radius matches up perfectly on that. So whenever I say pi r squared, it'll actually be pi y squared. So the integral, oops, I don't want to put the a to b. I think you know that. F of x squared. Oh, I forgot to do this as well. Let me go back and state something here. We're only doing a quarter of a circle on this one, so since it's a quarter of a circle, I need to have 1/4 pi r squared, so it'll be a 1/4 in the front. So this would be pi over 4 as my integral. Let me go back. I want to check something on the quartercircle. I'm sorry, in the semicircle. On the semicircle, I forgot to mention that this is only half of a circle. Half of a circle. So even though that this turns into 4 times 2, so actually this should be 8. That's my mistake there. All right, definitely make sure you go back, watch this video if you need to learn more about the formulas. This is basically the formulas that we're going to be using for the rest of this homework on Wednesday and Friday. Thank you.